Before solving the pendulum problem in this video, I want to provide a visual on how actually in practical terms this problem works. So here we have this little sphere, metal sphere, which is the bullet. We have the wood block, which is this piece right here. So those two are the main pieces of this particular problem that we are going to solve next. So this block is suspended by those strings, free to move. And now we have this bullet that is going to be fired when the trigger is being applied. So once we do that, we can clearly see as the bullet hit the block. So both together, they are going to rise in a vertical direction. And here is the ground zero. So the bottom of this pendulum is as a reference as a ground zero. So the block initially is stationary. The bullet is being fired with a velocity, basically 3 steps. One is this bullet is in with a speed, and the block is stationary. And then the second step, when the bullet hits the block. And the third one, they both together, they are going to rise and stop before falling down. So let me play the short video so you can have a visual about what this problem is involved. And comes back. Okay, so now let's check all the details about the problems. In this question, we are using conservation of energy and conservation of momentum to solve this problem. Description of this problem. A bullet of mass 2 grams is fired horizontally into a block of wood of mass of 600 grams. The block is suspended from strings so that it's free to move in a vertical plane. It is going to be fired horizontally, however, it's going to move in a vertical plane up. The bullet buries itself in the block, and the block and bullet rise together through a vertical distance of 8.6 centimeters, as shown in this picture. So the first question is, calculate the change in gravitational potential energy of the block and bullet. To analyze this motion, let's divide into 3 steps. Step 1, the bullet is moving toward a stationary block. The step 2, the bullet hits the stationary block. And step 3, the bullet and the wood, they move upward and stop before falling back down. On step 1 and step 2, the ground reference here is 0. There is no height. However, on step 3, both bullet and block, they rise to this vertical displacement from 0 to 8.6 centimeters. For this reason, we can use on step 3 conservation of energy, potential and kinetic energy. However, we cannot use the same approach on step 1 and 2 because there is no height in those 2 motions. With this in mind, sounds like we have a plan. So now let's label all the parts and identify the variables that we need to use in our sequence. The mass of the bullet is 2 grams. In kilograms, 0.02 kilos. The same we do with the mass of the block. Let's call uppercase M. In this case, because the bullet is inserted in the block, so now the mass, combined mass here is 602 grams or 0.602 kilograms. The height, which is 8.6 centimeters, we can translate into 0.086 meters. The first question is asking to calculate the change in gravitational potential energy of the block and bullet. So it's clear that we are going to calculate in step 3 because potential energy, we need height, and that's where we have the height. The change in gravitational potential energy we can represent by delta EP. The original formula for potential energy is the mass times acceleration of gravity, which is 9.8 meters per second square, and the height. In this case, because it's asking the change in gravitational potential energy, which means when the bullet and the block rise from 0 to 8.6 centimeters, rise vertically. So, and then we have the change in height to be final height minus initial height. Our initial height is 0. So in this case, all this is 0. So our change in potential energy is the mass of both together, which is 0.602 kilograms, times the acceleration of gravity, 9.8, and times the height in meter. So the change in potential energy after you plug in your calculator is 0.51 joules as a result. The following question is to show that the initial speed of the block and the bullet after they began to move off together was 1.3 meters per second. So in this case, we are going to use the conservation of momentum, which states that the energy at the bottom right here, the energy at the bottom is going to be equal to the energy at the top. So we have conservation of energy in those two steps. So why we're doing this? So if we need to find the velocity of both bullet and block rising together, we need to use the kinetic energy formula where we have the velocity right here. So we are going to use the conservation of energy. So the energy, the potential energy plus kinetic energy at the bottom is going to be equal to the potential energy and kinetic energy at the top of this motion. So let's review here on step 3. On step 3, the bullet and the wood, they move upward and stop before falling back down. So we are going to use this approach to define our potential and kinetic energy at the bottom of this motion and at the top of this motion. Please note here, when this stop, the velocity in this case is going to be 0. However, the initial here is not 0 because it needs this velocity to rise the motion, right? But we don't have height here because we are at ground 0. So because of this, our potential energy at the bottom is 0 and our kinetic energy at the top is also 0 because it stops. So what is left from this equation is the kinetic energy at the bottom is equal to the potential energy at the top. So since both bodies, the bullet and the block, they are together, so the mass, because the formula for kinetic energy is mv squared over 2, and the formula for potential energy is mgh. So since the body has the same mass, so we can cancel, and what is left here is v2 squared over 2 is equal GH. Doing cross multiplication here, our V2 square is equal to 2GH. And doing a square root on both sides. So now our V2 is 2 times G times H. So our G is 9.8. Our height is 0.086. And solving all this, we have the velocity, the block, and the bullet began to move off together, 1.3 meters per second, exactly how it's showing here. Now, on the question B, we are going to use the information, prior information, and the principle of conservation of momentum. In this case, that's what they want you to use. Determine the speed of the bullet before the impact with the block. Now, back here to our motion analysis, we are talking about step 1 and 2 now. On step 1, the bullet is moving with this speed, and the block is stationary. And both, they don't have any height. The ground reference here is 0, so we can use conservation of momentum. Remember, the conservation of momentum, P, is equal to the mass times the velocity of the body. So we have two bodies here. We have the bullet and we have the block. So we are going to calculate the individual momentum for the scenario. So before and after a collision. So we call collision because the bullet is going to hit the block and it is going to cause a motion because of that. So the initial momentum is the mass of the bullet times the velocity of the bullet plus the mass of the block times the velocity of the block. In this case, I'm just gonna write here M. The velocity of the block is 0 because it's stationary. So this is 0. So that's all that is left. Now, after the collision, what we have is that's momentum 2 after the collision, before and after. So after the collision, now we have both bodies together, the bullet and the block, and they are going to about to move with this velocity 2 that we calculate prior in this problem. So now we have 602 grams times the velocity where the block and the bullet start to rise the motion up. Now you may ask why I did not convert it to kilograms. Is because when you have a multiplication, equations that have multiplication here, and you are going to compare them, so you can eliminate the units. It will make it easier the calculation. So at the next step, we are going to make those two equations equal, and let's see what we get. Okay, so it will be 2 grams times V1. That's what I'm looking. And times, when you multiply 602 grams times 1.3, that's what we get. And the reason why I repeat the word grams here, because frequently grams, the symbol for grams, is there is a confusion between this and G for acceleration of gravity because it's the same symbol. So in this case, I just use the word gram, so make sure that you understand those two units are being canceled. And now our V1 is 782.6 divided by 2, which is 390. So this is a pretty high speed for the bullet. It kind of makes sense. The next question is asking to calculate the kinetic energy of the bullet just before impact. So in this case, we are considering just the bullet since the wood block is stationary. So the mass of the bullet in kilograms and the velocity of the bullet that we calculate prior. Now, why I'm not using 390 here is because this is my original results, and I always like to use the original one instead of the rounded one. So that is the speed of the bullet squared divided by 2. So that's the energy, the kinetic energy of the bullet before impact. Okay, so now we are heading to the end of this problem, and the question now is to state and explain what can be deduced from your answers to C, I, and AI about the type of collision between the bullet and the block. There are basically two types of collision. One is elastic collision, and the second one is inelastic collision. So there is a way to determine if it's elastic or inelastic based on the value of the kinetic energy before and after the collision. So that's going to be my approach to answer this question. For question AI, we calculate the energy just using the change in gravitational potential energy, which the result was 0.51 joules. However, at CI question, the kinetic energy is 153 joules. And now we are going to compare both energy and see what happened. On question AI, I show you that the energy was calculated using the potential energy, which was 0.51 joules. At this time, I'm using the kinetic energy for the same scenario. So prior on AI is talking about the block and the bullet, the change in gravitational potential energy. So I'm going to calculate here the kinetic energy for the bullet and the block using the speed that I calculate for the both together moving up, which was 1.3 meters per second. So the kinetic energy in this case is identical to the potential energy from AI. However, the kinetic energy from CI that is calculated on the previous question is 153 joules. So there is a difference between before and after in terms of energy. So in this case, the kinetic energy is not conserved, and this is an indication this is a inelastic type of collision. Basically, what I did here is that in order to compare apples with apples, kinetic energy with kinetic energy, so I calculate from AI the kinetic energy because we have in potential energy here. So I want to calculate in kinetic energy. We're using kinetic energy formula, and the second one was calculated prior, 153. So that way we can see there is a difference between both kinetic energy. So that's why, just to reinforce what I said, this is a case of inelastic collision because the kinetic energy is not conserved.